our discussion this day is all about probability. At the end of the discussion, everyone is expected to first define probability and then explain the terms experiment, sample space, event, and outcomes, and then describe the classical approach to probability, and lastly, calculate probabilities using the rules of addition and multiplication. So this time we will define probability. Probability is a value between 0 and 1 inclusive, describing the relative possibility. So if we talk about relative possibility, we are referring to the chances or likelihood an event will occur. It is frequently expressed as decimals such as 0.70, 0.25, or 0.50. However, it may be a fraction such as 7 over 10, 27 over 100, or 1/2. In other words, if we talk about probability, a number must be between 0 and 1, and then beyond that number is no longer the value of a probability. So the closer the probability is to 0, the more improbable it is the event will happen, and the closer the probability is to 1, the more sure are we to happen. This time, when we discuss about probability, we will encounter some of the keywords. First, experiment. This is a process that leads to the occurrence of one and only one of several possible observations. And then another keyword is an outcome. This is a particular result of an experiment. So we have our experiment wherein it is a process, and then outcome is a particular result of that experiment. And then we have also event. This is a collection of one or more outcomes of an experiment. And then lastly, we have here a sample space, also called sample description space or possibility space of an experiment or random trial, is the set of all possible outcomes or results of that experiment. So be familiar with these 4 keywords when we discuss about probability. That is experiment, outcome, event, and sample space. Now, to familiarize this word, we have here our example. When a dice is rolled or die rolling experiment, then when you roll a die, that is an example of an experiment. And then in a BOD or Board of Directors of SSCR, when you count the number of Board of Directors, then that is an example of an experiment. Now, when you roll a die, you will observe a number of 1, 2, 3, 4, 5, and 6. So these 1, 2, 3, 4, 5, and 6 are your possible outcome. And then, when you count the number of Board of Directors, you will observe as 2 are over 50 years old, 1 is over 50 years old. So this result is now our outcome or possible outcome. And then again, if we roll a die, observe an even number. Take note the outcome is 2, 1, 2, 3, 4, 5, 6, and then even number is 2, 4, 6. So we observe an even number, or maybe we observe a number less than 4. So this one, we have here what we call as some possible event. Okay. Now take note, this is different from possible outcomes, because possible outcomes, we observe a number 1, 2, 3, 4, 5, and 6. However, in some possible events, we observe an even number or observe a number less than 4. On the other hand, for the Board of Directors of SSCR, we observe some possible events by having this one: more than 5 are over 50, fewer than 5 are over 50. Okay, so that is how we differentiate the keywords, which is experiment, outcomes, and events. Now we go to the sample space. Example, what is the sample space for one flip of a coin? Now, if you observe, when you flip a coin, you will observe the heads and the tail. Okay, so these are an example of a sample space. Another example is, suppose I roll two six-sided dice. These are now the six-sided dice. What is the sample space for the possible outcomes? So if you observe here, you will observe this one as a sample space. So this is 1, 2, 3, 4, 5, 6. So we have here our sample space are 1, 2, 3, 4, 5, 6. Now, we will proceed with the word tree diagram. Tree diagram is a device consisting of line segments emanating from a starting point and also from the outcome points. It is used to determine all possible outcomes of a probability experiment. Example here, we have used a tree diagram to find the sample space for the sex of 3 children in a family. Remember, a tree diagram is the device consisting of line segments emanating from a starting point. It is used to determine all possible outcomes of a probability. Okay, so again, we go back to our example. Use a tree diagram to find the sample space for the sex of 3 children. So this is our example. So you have here your parent, and then a first outcome. Remember this one, we have here, use a tree diagram to find the sample space for the sex of 3 children in a family. Okay, so again, we read this one again. Use a tree diagram to find the sample space for the sex of 3 children in a family. Now, our outcome pertains to the sex of one child and the second child, of the next child, and the sex of the third child. Each of the children will correspond to branching in the tree. So, here is the question that relates to our example. What is the sex of the first child? Is it boy or girl? So, if you have noticed here, first child, is it boy or girl? Okay. Then next, given the sex of the first child, what is the sex of the second child? So if you look at this one, first child, second child. So if this is a boy may have a child which can be a boy or a girl. For the first child wherein the girl, this girl will have a result of having a child either boy or girl. So this is now the second child. Next, the third child. So this boy might result to have a boy and a girl. This girl may have a child which is boy or girl, and then this boy will have a child either boy or girl, and then this girl will have a child either boy or girl. So the outcomes now, here is the parents for the first child, second child, and third child. You have here B, B, B. These are boy, boy, boy. And then we have here another outcomes, boy, boy, girl. Then we have here another outcomes, which is boy, girl, boy, and then boy, girl, girl. So we have here another outcome. Now for these three, girl, boy, boy. So we have this one, and then girl, boy, girl. So we have this one. And then the other one, girl, girl, boy, and then girl, girl, girl. So we have this one. So these are now the outcomes based from our example. Now, we will proceed with the approach to assigning probability, which is in the classical probability. If we talk about classical probability, that is based on the assumption that the outcomes of an experiment are equally likely. The probability of the event happening is computed below. First, probability is equal to the number of favorable outcomes divided by the total number of possible outcomes. To discuss our classical probability, we have here our example. Remember, probability is the number of favorable outcomes divided by the total number of possible outcomes. So we have here, consider an experiment of rolling a six-sided die. So we have here our die. What is the probability of getting an even number of spots appear face up? So take note, a die will have a number 1, 2, 3, 4, 5, 6. So if we talk about even number, that includes 2, 4, 6. So there are three possible outcomes that even number will appear, that is 2, 4, 6. So the number of favorable outcomes is equivalent to 3 divided by the total number of possible outcomes, which is equivalent to 6. So our probability now of getting an even number is 3 over 6, or that is 0.5. So that is our example for a classical probability. Now, in our discussion about classical probability, we have here what we call as the term mutually exclusive. Mutually exclusive is the occurrence of one event means that none of the other events can occur at the same time. So we have here our example. An employee selected at random is either male or female, but not both. Okay? So if you notice, this is more on the sex of a person. He may be a male or female, but no dual sex, no? So that person can be a male or a female, but not both. So this is an example of mutually exclusive. Another example here is a manufactured part is acceptable or unacceptable. The part cannot be both acceptable or unacceptable at the same time. Now, that is what we call as that is an example of a mutually exclusive. None of the other events can occur at the same time. Now we have here another term for probability. We have what we call as collectively exhaustive. Collectively exhaustive, at least one of the events must occur when an experiment is conducted. So for the die tossing experiment, every outcome will be either even or odd. So the set is collectively exhaustive. If the set of events is collectively exhaustive and the events are mutually exclusive, then the sum of probability is 1. So in our discussion about probability, it is important for us to discuss Venn diagram. A Venn diagram is a visual way of representing probabilities. So we have here a simple probability. Probability of E and then probability of S is equivalent to 1. Take note, the maximum value for probability is equivalent to 1. So this one represents the probability of a certain object. Now this one, if you look at here, P of E and then P bar of E. So when we find the value of P bar E, that is equivalent to 1 minus the probability of E. So this is just a representation of a Venn diagram. So we have here some rules of computing probabilities. The rules of addition. First, we have what we call as the special rule and general rule. So when one event occurs, none of the other events can occur at the same time. So we have here the first event and then the second event. So if this is our Venn diagram, then this is a set and then this one is another set. Okay, so that is special rule. When one event occurs, none of the other events can occur at the same time. That is the special rules of addition. And so we have here the general rule of addition. When one event occurs, other events may occur at the same time. So we have here this one event and then the other event. So we have here the common. So in set theory, we have this one as the intersection. Okay, intersection. Now, the special rule of addition. To apply this rule, the event must be mutually exclusive. So, probability of A or B is equivalent to the probability of A plus the probability of B. Plus, of course, if there are other, let's say, set, so let's say C or D. Okay, so for this case, that is probability of A or B, so equals probability of A plus probability of B. Now, the following Venn diagram represents mutually exclusive concept. There is no overlapping of an event. So this is an event A, event B, and event C. So this is an additional information regarding Venn diagram. So we have here our example about mutually exclusive or rules of addition. An automatic show machine fills plastic bags with a mixture of beans, broccoli, and other vegetables. Most of the bags contain the correct weight, but because of the variation in the size of the beans and other vegetables, a package might be underweight or overweight. A check of 4,000 packages filled in the past month revealed that the weight wherein we divide the weight as underweight, satisfactory, and then overweight. So if we talk about satisfactory, it is not underweight and not overweight. So that's the weight. And then the event represented by A for underweight, B for satisfactory, and then C for overweight. Now the number of packages for underweight, we have here 100. The number of packages for satisfactory, we have here 3,600. And for overweight, we have 300. So a total of 4,000 packages. So if we compute the probability of occurrence, then for underweight, we have here there are 100 packages divided by the total packages, which is 4,000. So that is equivalent to 0.025. For satisfactory, the probability here is 3,600 divided by the total, which is 4,000. That is equivalent to 0.900. For the probability of overweight, that is 300 divided by 4,000. So that is equivalent to 0.075. So, what is the probability that a particular package will be either underweight or overweight? So, we will write here as probability of A, which is represented by our underweight, or C, represented by overweight. So, if you look at this one, probability of occurrence for underweight is 100 divided by 4,000. You have this one. And then 300 divided by 4,000. So this 100 divided by 4,000 is the underweight, probability of underweight, and then this 300 over 4,000 is the probability of occurrence for overweight, since we are going to find the probability of underweight or overweight. So when we add this one by rules of addition, that is equivalent to 0.10. Note that the events are mutually exclusive, meaning that a package of mixed vegetables cannot be underweight, satisfactory, and overweight. Furthermore, we have here what we call as complement rule. So in complement rule, the probability of A is equivalent to 1 minus the probability of not A. So we have here the probability that a bag of mixed vegetables selected as underweight, so we have here P of A, plus the probability that it is not an overweight bag, written as P not A, and read as not A must logically equal to 1. So from example 2, show that the probability of a satisfactory bag is 0.90. So look at this one, satisfactory is 0.90. So we will show we will prove this one as 0.90 using a Venn diagram, or by its calculation using complement rule. Okay. So our formula for complement rule, okay, before we discuss this formula, we will have this diagram first. So the probability of A is 0.025. This one. Probability of A is 0.025, so represented by this one. And then probability of C is 0.075, this one. And then not A or C, that is equivalent to 0.90. Not A or C. This is A, this is C. So not A or C, this yellow color, that is 0.90. Now if we make use of our formula here for complement rule, probability of B, take note B is satisfactory because we are going to find out the probability of not A or C. So which is equivalent to 0.90, no? So probability of B equals 1 using this formula minus the probability of A plus probability of C. This probability of A plus probability of C is not, not A or C is what we call as satisfactory, which is B. Okay, so we go back to this one. 1 minus probability of A plus probability of C. So by looking at this formula, that is not probability of not B, this one. Probability of B equals 1 minus the probability of not B. Since this is not B, which is equivalent to probability of A plus probability of C, so we simply add their value, then the result is 0.90. So this is our proof. Now, the general rule of addition. The outcomes of an experiment may not be mutually exclusive. So we have here to illustrate, suppose the tourist commission selected a sample of 200 tourists who visited to some tourist attraction last year in Luzon. The survey revealed that 120 tourists went to Enchanted Kingdom and 100 went to Star City. What is the probability that the person selected visited either Enchanted Kingdom or Star City? Using the special rule, we have here the probability of Enchanted Kingdom or Star City, that is equivalent to, so since there are 120 tourists went to Enchanted Kingdom, so 120 divided by 200 plus 100 went to Star City, so we have here 100 divided by 200. 200 is the total tourist, okay, visited the attraction. So if we sum up their probability, 120 divided by 200, that is 0.60, plus 100 over 200, that is equivalent to 0.50, which is also equivalent to, when we sum this up, that is equivalent to 1.10. There is no probability greater than 1. Take note, our probability ranges from 0 to 1. Since this is 1.1, then there is no probability equal to this one. So it happens that many tourists visited both attractions and are being counted twice. A check of survey revealed 60 out of 200 visit both attractions. In other words, for 120 and 100, 120 tourists for Enchanted Kingdom and 100 to Star City, there are 60 tourists visited both Enchanted Kingdom and Star City. The result will be 0.80. So when two events both occur, the probability is called joint probability. The probability that tourist visits both attractions, that is 0.30, is an example of joint probability. This 0.30 is the result of 60 over 200. So by Venn diagram, this one represents the probability for Enchanted Kingdom. The probability of tourists entering Enchanted Kingdom, and then this one is the probability of tourists entering Star City. And then this one is the probability for both for tourists visited both Enchanted Kingdom and Star City. So since we mentioned about joint probability, then joint probability is defined as a probability that measures the likelihood two or more events will happen concurrently. So the general rule of addition is probability of A or B equals probability of A, we have this one represented by green in color, plus probability of B represented by red in color, minus probability of A and B, we have this yellow colored. So that is what we call as joint probability. So we have here our example. What is the probability that a card chosen at random from a standard deck of cards will be either king or a heart? So take note, in a card, there are 52 cards. Out of 52 cards, we have this one, 52 cards, there are 4 flowers. That includes heart, diamond, spade, and globes. So there are 4 flowers. So going back to our example, what is the probability that a card chosen at random from a standard deck of cards will be either king or a heart? So when we solve its probability, we have here probability of king is equivalent to 4 over 42 because there are 4 kings in a deck of 52 cards. Same with heart, the probability of heart, there are 13 hearts out of 52 cards. So 13 hearts in a deck of 52 cards. That is the probability of heart. Probability of king of heart, this one. So this king of heart is 1, only 1, divided by 52 cards. So 1 king of heart. Does the king of heart, does the king or heart, so this is now what we are looking based from the problem. We go back to this problem. What is the probability that a card chosen at random from a standard deck of cards will be either king or a heart? So we have this final solution. The probability of king or heart is equivalent to, so king is 4 over 52. We have this one, plus 13 over 52, that is the probability of a heart. We have this one, minus probability of king of heart. That is 1 over 52. This king of heart is the king or heart is common. We have this one. We have our king, that might be king and heart. And then we have here our heart, which might be king and heart also. So this is our common. So we will subtract this common, that is 1 over 52. So our value is 0.3077. Now we have the rules of multiplication. So we have done with the rules of addition. This time we will proceed with the rules of multiplication. In the rules of addition, we find the likelihood of combining two events. In the rules of multiplication, we find the likelihood that two events both happen. So we have here the two rules of multiplication, the special rule and the general rule. Special rule is that two events are independent. We assume that events A and B occurs at different times. Whereas general rule, two events are dependent. So we have here the special rule of multiplication. Two events A and B are independent. If we talk about independence, the occurrence of one event has no effect on the probability of the occurrence of another event. So the special rule of multiplication, we have this one. The probability of A and B is equivalent to the probability of A times the probability of B. That is the special rule of multiplication. So we simply multiply their probabilities. So we have here our example. A survey by the American Automobile Association revealed 60% of its members made airline reservations last year. Two members are selected at random. What is the probability that both made airline reservations last year? So we have here our solution. the probability of A and probability of B, because we are talking here about two members are selected at random, so both made airline reservations last year. So probability of A and then probability of B, wherein probability of A and probability of B is equivalent to 0.60 times 0.60, because we have here from our problem, a survey by the American Automobile Association revealed 60% of its members made airline reservations. So that is 60%, that is 0.60. That is for probability of A, since A here is two members are selected at random, including A and B. So one member is A, its probability is 0.60, the other one is 0.60, which is then equivalent to 0.36. That is the probability of A and probability of B. We simply multiply their probability. And then letter B, neither member makes a reservation. That is the probability of A and probability of B, not B, which is then equivalent to probability of not A multiplied by probability of not B. So if this is if the probability of A and B is 60.60, then the probability of not A is 0.40, since 1 minus 0.60, 1 is 100%, 60%, 40%. Okay, so 40 times 40, that is equivalent to 0.16. Okay, so we will proceed with the general rule of multiplication. Two events A and B are dependent with each other. So we have here our joint probability, the probability of a particular event occurring given that another event has occurred. So the general rule of multiplication is equivalent to probability of A and B is equivalent to probability of A times the probability of B minus A. So we simply subtract if we have what we call as the joint probability. So to discuss this one, we will have this example. Example number 6. A golfer has 16 golf shirts in his closet. Suppose 9 of these shirts are white and the others blue. He gets dressed in the dark, so he just grabs a shirt and puts it on. He plays golf 2 days in a row and does not do laundry. So we have this one as the 12 golf shirts. We have here 9 are white and then 3 are blue. So take note, he gets dressed in the dark, so he just grabs a shirt and puts it on. He plays golf 2 days in a row and does not do laundry. What is the probability that both shirts selected are white? So first selection is white. Since there are 9 whites out of 12, then we have here probability of white and white. So first white is 9 over 12. And then after selecting one shirt, of course out of 9 it becomes 8. And then the total now is 11. So we will multiply that 8 over 11 for the second selection of a shirt. This 9 over 12 is the first selection of a shirt, which is white, and then second selection is 8 over 11. 9 subtracted by 1, that is 8, and then 12 subtracted by 1, that is 11. So our probability of white and white, first selection and second selection, that is equivalent to 0.55. Next question, what is the probability that 3 white shirts without replacement? So probability of white and white and white. So first selection is 9 over 12. Second selection is 8 over 11 because we already select 1. So this is deducted, 8 over 11. And then another selection, the third selection is 7 over 10. So that when we multiply this value, that is equivalent to 0.38. So without replacement. Okay. Now, third is what is the probability that both shirts selected are blue? Remember blue, we have here 1, 2, 3. So that is, first selection is 3 over 12. Second selection, since we select already one shirt, so there are 2 left, 2 more blue left. So 2 over 11. So that is the probability of B blue and blue is equivalent to 0.049. Okay, so that is our example for joint probability. So to sum up, here is our summary of probability rules. Addition rule 1, if two events A and B are mutually exclusive, then we have here probability of A or B equals probability of A plus probability of B. Addition rule 2, for any two outcomes A and B, we have here the probability of A or B equals probability of A plus probability of B minus the probability of A and B. Next, we have multiplication rule number 1. When two events A and B are independent, then the probability of A and B equals probability of A times probability of B. So we simply multiply their probabilities. And then multiplication rule number 2. When two events are dependent, the probability of both occurring is probability of A and B is equivalent to probability of A times probability of B minus A. So this is now the summary of our discussion about probabilities.